When you're working with paired data, so x, y, you can compute a correlation coefficient for the two variables. Now, typically, the observations that you have for the x values are a sample of the random variable x, and the corresponding observations that you have for the y values are the paired sample for the y random variable. And so this is in fact a sample correlation coefficient. The relationship is fairly easy to compute. It is the sum of the value of xi minus the sample mean of the x values that I have times the value of the yi's minus the sample mean of the y values that we have. So this is a product here. Eventually, some of your next courses, you might recognize that this is meant to be an approximation for the covariance between the variables x and y. But at the very least, that this is proportional to the covariance between x and y. That's for the numerator. The denominator is the square root of, this is an expression that we recognize. This is almost the sample variance, except in the sample variance we'd be dividing by n minus 1 in both of these cases here. So this isn't quite the sample variance, the sum of the squares of the differences between the observation xi's and the sample mean x. This is almost the variance, the sample variance. And this is multiplied by an expression which is almost the variance of the y random variable. Now we'll have to write these expressions quite a lot, and so in order to keep things simple, we're going to use a shorthand notation. Sxy, that actually stands for this expression. Sxx stands for this one. Syy stands for this one. And so the coefficient of correlation, the sample coefficient of correlation, is the ratio between Sxy and the square root of the product of Sxx and Syy. This is, of course, only well defined if both Sxx and Syy are different from 0. If they're equal to 0, then you're dividing by 0, and this is not well defined. Well, when is Sxx equal to 0? It's going to be equal to 0 if the sum of non-negative quantities is equal to 0, and the only way that this can happen is if all of the terms that are being added are actually equal to 0, which would mean that all of the observations are constant. All of the xi's take on the same value, and all of the yi take on the same value. So as long as there's at least two different points, xi, yi, where the x's don't take the same value and the y's don't take the same value, then the coefficient of correlation will be defined. The sample coefficient of correlation, of course, in this case. If the sample correlation coefficient is 0 or very small, because in practice it'd be very difficult to get it to be equal to 0, we will say that the variables are uncorrelated, that they do not have a correlation. And if the coefficient is not 0, or if the absolute value of the coefficient is large, we'll talk about what large might mean in a second, then we say that the variables are correlated. It is not explicitly stated here, but the correlation is a linear correlation. I'll talk about what that means in a second. For the data that we've been given in the previous section, the quantities that we have, Sxy takes on the value 10.18, Sxx takes on the value 0.68, Syy takes on the value 173.38, and so the coefficient is 0.94. One thing we'll notice is that the coefficient is unaffected by changes of scale or origin. If you add the same constant to all of your x measurements, that does not change the value of x minus x bar. Same thing with y minus y bar. And if you multiply x and y by some constant, well, that's going to change both the numerator and the denominator equally, so you can rescale the data, you can center it, and you're going to get the same coefficient of correlation. Another thing to keep in mind is that the coefficient is symmetric. If you flip the axes, if you decide to write instead of the standard xy, yx, the coefficient of correlation will take on the same value. Another thing to notice is that no matter what data you're using, the coefficient of correlation can only ever take on values between -1 and 1. And the only time it can take on the extreme values, -1 and 1, is if all of the observations are actually on a line, but either positive or negative slope. The correlation here would be 1, whereas the correlation here would be -1. The sign that is taken by the coefficient of correlation gives you an idea about the trend of the points, whether the points are trending upwards, so when you increase x, does y increase, or downwards, when you increase x, does y decrease. Now, when you find that there's a high correlation coefficient value between two variables, that doesn't necessarily mean that there's a causal relationship between the two variables. All you have found is that in your observations and the data that you've collected, an increase in one is accompanied by an increase in the other, or an increase in one is accompanied by a decrease in the other variable. But the accompaniment isn't necessarily a causal relationship. And it's possible for x and y to have a very strong relationship, but if the relationship is not linear, then the coefficient of correlation will not reflect it. Here, the observations that we have suggest that the relationship between x and y is quadratic. I would expect to see something like, that's a pretty strong relationship. That's a powerful statement to make, to say that x and y are actually related this way. But the coefficient of correlation is likely to look like this. Basically be 0, or at least very small, -0.12. Whereas on the right here, there is a strong relationship, which is roughly speaking cubic relationship. And if you compute the coefficient of correlation, you will find that there's a pretty strong relationship. When x increases, y tends to increase as well. It doesn't do so linearly, it does so with a weird structure, but it certainly seems to follow this pattern. So even though this doesn't follow a linear pattern, there is still a fairly strong linear component to the relationship, and that is captured by the value of the coefficient of correlation, which is 0.93. So the values range from 1 to -1. A 1 means that you have a perfect positive correlation. They all lie on a line with a positive slope. 0.9, you would see some noise, some variation, but all in all, it looks as though there is a positive line trend. 0.5, you still have, roughly speaking, a trend, but there's a lot more noise. It's starting to look like a cloud. By the time you get to a correlation of 0, this is one of the ways in which you can get a correlation of 0. It's just a diffuse cloud. No preferred trend, no preferred direction. Just looks like a blob. And then if you go through similar correlation values, but negative side of things, you'd get a low negative correlation. There is definitely the suggestion of a negative trend, but a fair amount of noise. -0.9 would give you very strong suggestion of a negative trend, very little noise, and at -1 you have a perfect line with a negative slope. So in our case, the data that we have, if we look here, we have a strong indication of a linear trend, not that much noise, all things considered, and it is not surprising then that the coefficient of correlation would be 0.94.